On a case study of.
Hi friends, today we are going to discuss a case study on hardware software code design approach. Here we have taken a topic based on cryptography, how cryptography is working with the help for hardware software code design approach. So our topic is based on coding and cryptography for resource constrained wireless sensor networks, for how this work will be done in hardware software code design approach. This is presented by myself, Mera Shravya, my friends Elizabeth Kadayala and Basani Revati. Let's talk about this case study briefly with the help of cryptography concept. First, our main objective is that with the help of wireless sensor networks gained a lot of attention in recent years due to their widespread applications potential. With the help of wireless sensor networks, we are going to discuss the cryptography concept. In cryptography concept, we are talking about private and public key. These are the basic topic based on cryptography. With the help of these keywords, the block coding has potential candidates to address. With this cryptography concept, we'll talk about hardware software code design. The design issues related to sensor networks by considering public and private key cryptography. This is the main issue in this paper, in this case study. So in particular, we'll consider architectures which could be easily adopted to various protocols. Here we will discuss about some type of protocols also. The introduction of the paper is based on embedded systems found many applications such as automotive industry, control, medical systems, agriculture, wireless communications, household, so on. These constraints refer to power consumption, area of implementation, speed of operation, reliability, and time to the market. This point refers to that how cryptography work in code, hardware software code design. In hardware software code design, we'll talk about the area, how to reduce the area, how to reduce the time complexity of the architecture, and so on. All these constraints have to be respectedly while keeping very low cost of the system. Both hardware and software are crucial to maintain a good balance between so many constraints. The general perception is that the low cost and the fast time to market can be maintained if the system can be implemented in the software. Due to real-time system constraints, it is possible that a software implementation would not meet the speed and power consumption constraints. Therefore, it would be necessary that parts of the software implementation will be migrated to hardware. For our implementations, hardware means both FPGA and ASIC implementations, while software runs on an 8-bit microcontroller. With the help of FPGA and ASIC, we'll talk about the case study. In some applications which require security, it is imperative that one takes into account other constraints such as resistance to various attacks either on the communication protocols or cipher themselves. For such systems, it is widely accepted that hardware offers more protection as customized defense could be hardwired in the underlying logic. In this paper, we'll present some methods of building a secure and reliable wireless sensor network infrastructure which relies on both hardware and software. Security related issues as well as implementing a reliable communication between various nodes. A careful partitioning between hardware and software is that necessary such that the best trade-off between the cost and performance is obtained. We'll take more care on hardware and software to obtain the best cost and performance. Topics such as reliability, security, and reducing power dissipation in such systems has received considerable attention in the recent years. This is simple basic architecture of generic system. Here we have 8 or 16 or 32-bit bus. For this bus, we have connected microprocessor, memory, hardware, accelerometers in the sense FPGA and ASIC. Input and output of RF, DAC, ADC, antenna. With the help of these blocks, we'll design an architecture so that our hardware and software code design is worked, how it has worked for cost to reduce the cost and performance. Error control coding is necessary to improve the reliability of a communication links within the network. Security in wireless sensor networks has lately received increased attention.
Hi, this is Revati. I am going to explain how the presentation of the 20mm platform is. The 25mm Cube platform developed at Tyndall National Institute is a versatile platform which allows the implementation of very complex algorithms and architectures, and also the exploration of the hardware-software codesign methodologies. The system incorporates a radio receiver in the 2.4 GHz ISM band designed to minimize the power consumption and maximize data throughput. Additional input capability for sensor and actuator integration can be incorporated seamlessly due to the modular nature of the system. The embedded microcontroller for this platform is the Atmega 128L. This is an 8-bit microcontroller with 128K bytes in system programmable flash. The user can easily program the device with custom protocols. The Atmel microcontroller can be programmed to operate in sleep or power down mode, awaiting activity and interrupt pin. The wireless transceiver consists of fully integrated frequency synthesizer, a power amplifier, a crystal oscillator, and a modulator. Current consumption is very low, and a built-in power down mode makes dynamic power management easily realizable. This feature is also helping us to quantify the benefits of various error control coding used by keeping the lowest output for this transceiver and measuring the range of communication. This is the block diagram how the Xilinx Pardan is connected to the Atmega microcontroller and to that of the transceiver, and how the communication can be made. The transmitter receiver modes are there. This is the antenna and the noise channel is present. The FPGA is a low cost, low power Xilinx Pardan 2E family. The relatively large gate count allows us to prototype very complex architectures for both coding and cryptography. The mode allows also easy interfacing with various sensors by providing some standard connectors as well as ADCs and DACs. A fully stacked version of the model is presented. Depending on the requirements of the specific applications, new layers can be added to the mode in an easy fashion. The design space exploration. This is an example of wireless sensor network. In order to keep synchronization issues under control, each node in the network operates on a fixed clock frequency of 4 MHz. This allows us to simplify the optimization of the system in both hardware and software. By choosing the platform, our exploration is limited to finding versatile algorithms and partition this functionality between hardware and software. Given the platform described in the hardware is more suitable for implementing cryptography primitives, the proximity of the microcontroller next to the antenna also suggests the software will be mostly used to implement the communication protocols and error control schemes. That is the example we have taken wireless sensor network. My friend will explain the remaining part.
This is Elizabeth. Now I will explain the versatile implementation of error control coding. First we present a versatile architecture for a universal Reed-Solomon decoder. Universal Reed-Solomon decoder, it's a encoding of relatively easy, and it is based on linear feedback shift register architecture. This architecture is suitable for both hardware and software implementation. The Reed-Solomon block is on a Spartan 3 board, FPGA board. It is sliced into 6500 slices, and the software is also implemented on the same block, and the memory is of 5200 bytes of flash memory and 380 bytes of SRM. In the recent years, a new powerful coding scheme is emerging due to its error correlation capability. The low density priority check codes have outer performance many block scheme, and for a long length they approaches the Shannon limit. We analyze the potential of this code within sensor network application and present the ASIC realization. Next we'll talk about a public and a private key. Now here I'll explain about the public key cryptography. Security is a major challenge for sensor network. Data with various security levels is sensed and transmitted wirelessly. Due to their constraints in computation, memory, time and power resources, there is a susceptibility to intercept of the data by the unwanted party. We consider a Rabin scheme as a potential candidate for public key cryptography for our system, and we discuss the suitability of implementing this scheme on 25mm platform, in particularly on FPGA. Due to potentially sensitive nature of the communication between the sensor nodes, the confidentiality and the integrity of data must be assured. Both can be achieved by encrypting the communication. Security in wireless sensor network is mostly provided through symmetric key cryptography. Private key crypto system needed complicated key scheduling algorithm is established symmetric key. It is widely believed that the complexity cost of public key algorithm make them unsuitable for resources constrained application. In our system, we propose a public key cryptography architecture based on a Rabin scheme that provides efficient cryptography for data. This is the Rabin scheme. In a private cryptography, parties which intend to communicate must agree the secret symmetric key. This is currently achieved by embedding session key within the sensor nodes before they are deployed. In this scenario, the capture of a single node by an adversary may compromise the security of an entire network. Using public cryptography, we can overcome this difficulty by eliminating the necessity of the predetermined session key. Here it's a remote node and it's a base station. It's a plain text, and the plain text is it is encrypted, and the encrypted key is sent for the base station to for decryption, and the key is generated. And the generated key is sent for a cyclic process of encryption and decryption. Next, this is what all about the encryption and decryption of a public and a private key. Here's a conclusion. We have explained everything about the how the public key algorithm is selected and a private key algorithm has been selected. The Rabin scheme is selected for the public and the private key. The conclusion is that with exhausting all the possible coding and cryptography scheme, we present some issues related to reliability and security of communication within a sensor network, which is built using a hardware-software co-design approach. We present several realizations of coding and cryptography architecture which are suitable to be integrated with or mapped on a 25mm cube platform. Cost efficiency will play a key role in determining the extent to which security primitives will be incorporated in next generation sensor nodes. Fault tolerance is yet another crucial aspect of any security protocol. Given the nature of their use, sensor nodes are susceptible to physical impairment. This means that when whatever security protocol is devised, it should incorporate some degree of redundancy. We show that it is possible to adopt Reed, Solomon and LDPC codes to suit sensor network requirements. However, some careful partitioning is required to achieve the best performance cost versus cost trade-off. Security is a very expensive task due to complex computational and memory requirement. In this paper we have explained everything. We have explained some results implementation of two scheme suitable chosen platforms. Future work will include the crypto analysis of the proposed system as well as automation of the design flow of the sensor networks. And acknowledgement. The author wishes to acknowledge the importance of Ambient Electronic System Group from Tyndall National Institute. Part of this work we also support by SFI under National Access Programme and Enterprise Ireland. Thank you.
Thank you. I think you people something know about cryptography so that you can understand how the cryptography work on hardware software code design approach.
Thank you.
Done.